Welcome to the course on statistical mechanics of phases and phase transitions. In this lecture, we will continue our discussion of the interaction particles model that we started in the last lecture. So it's a good idea to briefly recap what we did. So our goal was to obtain the liquid gas phase boundary, and we started discussing a model which had hard sphere particles of radius r0 which were interacting with some 1 over r to the 6 potential determined by an energy scale u. We went on to see that if you are in the high temperature low density regime, you have a small parameter in the problem which is n naught, the density given to us, times the de Broglie wavelength to the power d. That turns out to be a small parameter in the problem, and we can expand the equation of state in this small parameter. We worked out what will be the answer if you expanded it up to this order in n naught lambda to the d, and we got the equation of state, namely the dependence of pressure on these quantities. We've also understood how to calculate this coefficients A1 and A2. A1 was just 1 coming from simple ideal gas kind of picture, and A2 was determined by two particle physics, two body physics. So in this lecture, what we will do is we will actually compute the coefficient A2, and you will see that there are some very interesting things in that computation. And we will, once we have computed A2, we will get the equation of state, and then in a sense we will be making our attempt to derive the phase boundary and all of that stuff. So the outcome of this lecture will be is that we would have uncovered the liquid gas phase diagram. Okay, so the interacting particles model, I have a set of particles of mass m in a d-dimensional periodic box of volume L to the d, and it is at some given temperature and some given density n0. These particles are interacting via a pairwise interaction u of r, where r is the distance between the two particles, and you can think of them as hard spheres, some radius r0, and an energy scale u which determines the attraction if they are at a distance greater than some number times r0. The dimensionless coupling constants, as we uncovered in the last lecture, are n naught lambda to the d. So this is high T low density, so that's a nice small parameter that we will have. R0 by lambda, or the cutoff by lambda, the hard sphere radius by lambda thermal de Broglie wavelength, and then this u divided by T, the interaction energy scale divided by temperature. And the virial expansion is what I have shown here, and we found that A1 is 1 and A2 is minus 1 by Z1. This is a single particle partition function multiplied by Z2, which is the two particle partition function with interactions, minus 1/2 Z1 square, and Zn is of course the n particle partition function. So let's calculate A2. So A2 is of course this quantity, minus 1 by Z1, Z2 minus 1/2 Z1 square. So let's start by computing Z2. Okay, so let me walk you through this calculation. Z2 is the partition function of two particles which has two pieces. The first piece here is an integral over the d-dimensional momenta of the particles, and so you'll end up getting the standard ideal gas like calculation working out here, so that's very easy to calculate. The second piece, so I have calculated that, and that just turns out to be 1 by lambda to the 2d. The second piece is determined solely by the interaction between the particles. So what does this look like? It looks like integral over the positions of both particles, so dr1, dr2, so the volume elements corresponding to the positions of the particles, exponential the interaction potential which is determined by the distance between the two particles, divided by temperature. How do we evaluate this integral? So, there is a very nice trick. So, we know that this potential depends only on the distance between the particles. So, what I do is I make a transformation of variables. I choose capital R as the center of mass between as the center of mass coordinate of these two particles, and small r is the vector connecting the two particles, the relative coordinates of the two particles. So, now we can show, it is a very simple calculation to show that when I do this integral over dr1 and dr2, after this variable transformation, you should compute that there is a Jacobian for this transformation, and you will see that the Jacobian is actually identity. You will see that there is a simple integral over this r, the capital R, which is the center of mass coordinate, and that center of mass coordinate can be anywhere in the volume V. And so, the integral over the center of mass coordinate will simply give me volume V. And I am now going to use the fact that this quantity, which is integral over the relative position dr, the integrand of this depends only on the distance and not on the direction of r. And what I am going to do is I am going to convert this integral. You can sort of imagine that there is certain spherical polar coordinates or some generalization of that in d dimensions. And so, what this integral will turn out to be is SD, which is like the surface area of a d-dimensional sphere, SD, and we can compute that exactly, and that is shown here. And an integral over the radial coordinate, the radius or the radial distance. So, that is dr, no vector here, it is not, it is a light font, so it is not a vector, and r to the d minus 1, this is just the shell volume element that you need, e to the minus beta ur. Okay. So, taken all of these taken together, you will see that Z2 that we started off working out is exactly equal to this result, which is SD, which is this quantity here, the surface area of d-dimensional sphere, multiplied by the volume divided by 2 times lambda to the 2d times this integral, which is an integral over the potential. Okay. So, before you try to do this calculation, let us see what are we up for. So, remember that A2 has to be a dimensionless number, and the dimensions number, even if you take the thermodynamic limit, so say you take V going to infinity, should remain some finite dimensionless number. Now, we know this is a ratio of this quantity Z2 minus 1 half Z1 square divided by 1 by Z, that is divided by Z1. Now, remember Z1 is a partition function of a single particle. Therefore, Z1 will be proportional to the volume. Now, if you look at say Z2 alone, you should, if you want a finite answer in the thermodynamic limit, Z2 should also naively depend only on V. It should be linear in V. It should be, that is proportional to V. It should not have a V square term. Because if I had a V square term, if the numerator had a V square term, then I will find that A2 is proportional to V, which will make no sense. So, let us now, keeping this in mind, let us try to do this calculation. So, you will immediately see that our calculation for Z2 will run into trouble. Why does it run into trouble? So, you look at this expression. This is what is e to the minus beta u of r, that is this expression here, this term here. So, I put the value of u of r which we had shown in a couple of slides back, which is minus little u times r0 by r whole to the 6. So, I just take that and stick it into the expression, and you will see that the integrand, this exponential integrand of this, it goes to 1 as r goes to infinity. So, now you will see that this will turn out to be proportional to the volume of the box, because you know when I go to very large distances r, this integrand is becoming 1. So, it is as if it is just integral dr r to the d minus 1, which actually gives you the volume of the box. So this suggests that Z2 by itself is proportional to V square, which may not be wrong, but it is a problem, because how are we going to cancel, but we need that the numerator is proportional to V, so that the denominator Z1 which is proportional to V will, the V from the numerator and the V from the denominator will cancel, and you get a finite answer for A2. So you may be a little taken aback by this, but rest assured that all is not lost. So here's a very nice sort of trick that you can do to perform this calculation and get nice physically meaningful results. I'll walk you through this. So the first observation is that 1/2 Z1 square, which is the partition function of two non-interacting particles, please check this, can be written in terms of the partition function of two interacting particles by simply putting R0 equal to 0 and U equal to 0. So my claim is that there is a different way of writing the partition function of two non-interacting particles by turning off the interactions in the problem with two particles. So what will I get now? So I have already found Z2 in the previous slide. I copy that down here, that Z2 is SdV by 2 times lambda to the D, and this stuff here. And I have now become a little bit more careful. I now know there is a hard sphere constraint. So I start the integration of Z2 from R0 and go all the way to infinity. Okay. And then this dr, r to the d minus 1, this whole thing is what we had for e to the minus beta u here. I am just sticking that in here. And now what I do, I take the same expression that I have and I put r0 equal to 0, which gives me the lower integral equal to 0. I'm substituting for 1/2 z1 square by this expression. So I have to take this term and simply put r0 equal to 0 and u equal to 0, which means I'll simply get integral 0 to infinity dr r to the d minus 1. Okay, this is getting to be interesting, because now I observe that this integral 0 to infinity can be broken up from 0 to r0, and the remaining part from r0 to infinity can be combined with this particular term to get me two pieces in my answer, which is r0 to infinity of this quantity e to the beta r0 by r to the power 6 minus 1 minus this quantity, which you will see is sort of proportional to the volume of a d-dimensional sphere of radius r0, right. So that's why you get this. And what I'm now going to do is I'm going to assume that the parameter u is very small compared to temperature. So beta u is a small parameter, and I am going to get contributions, from distances from r0 to infinity. I simply expand this and keep linear terms in beta u. Okay, that is an approximation, but it's a reasonable approximation. Okay, so I will end up getting this, and both of these integrals, now we have already mentioned about this integral can also be done exactly and fairly trivially, and the final answer you will get for z2 minus z1, as you can see very nicely, is proportional to V and is related to the dimensionless parameters of our problem in this fashion. So now if I just divide this quantity by z1, which is V divided by lambda to the D, you will find a very nice expression for A2, which is some dimensionless numbers which are dependent on space dimension, a parameter that is determining the strength of the attractive interaction, namely beta u. This was one of the dimensionless parameters that we had identified, and r0 by lambda, which was another dimensionless parameter that we had promised will appear in A2. So we have now shown that this A2 is a function of the dimensionless coupling constants or energy scales in our problem. Okay, so now we have an explicit expression for A2. So, this calculation is interesting, but if we stop here, of course, we will not see the physics. So, now we have to take this A2, put it back in our equations of state, and we have to see what physics this calculation will bring us. Okay. So, I am going to go to the equation of state now. So, I am going to take this calculation of A2 and stick it into my equation of state as I have shown here. This is like truncated virial expansion. So, P by N naught T is now 1 minus SD times this set of quantities R naught to D, and I kind of slightly reparameterize my equation of state. To reparameterize my equation of state, or to rewrite my equation of state, what I am going to do is I am going to take the terms that are here and I am going to define some new constants. So, there is this quantity which I will call A, and that quantity is this, it is proportional to the strength of the attractive interaction, and it is also proportional to the volume of the hard sphere, etc. And B, which is this quantity, which is directly the volume of the hard sphere. Okay. Now, to rearrange the equation of state in a suggestive way, I am going to define a new variable. This is what I call specific volume, which in these set of slides will be denoted by little v. So, that is 1 by N naught. If I do that, I will see that I will get this equation of state. You will see that I have rearranged these expressions and used A, B, etc. with these definitions, and I will get this expression. And you will see that up to order N naught square, these two terms are identical. So, what I had 1 plus B N naught, and you can see that that is the first term in the expansion of 1 by 1 minus B N naught. And so, I retain it in this form. Why am I retaining it in that form? Because you see that that is same as the something that you would have seen before. The pressure is T by V minus B minus A by V square, and that is just the van der Waals equation of state. So, what we have managed to do is we have started our study using the interacting particles model. We found a low density high temperature expansion, and from there we computed the equation of state, and lo and behold, we come up with the van der Waals equation of state, which we know is phenomenologically true because many interacting gases, so called non-ideal gases, can be described by the van der Waals equation of state. So, we started from a microscopic description of nature, namely we started by saying that there are atoms and they are interacting, and there is something called temperature which influences the physics of these atoms and so on, and from there we were able to compute this equation of state. So, I am sure all of you have seen this equation before. So, this is discussed in many elementary courses, both in physical chemistry, in physics and so on. And so, we know that this is the statement here is that the pressure is determined, has two effects. One is there is an excluded volume. So, when I have hard sphere, so remember B is simply the volume of the hard sphere. So, there is a certain excluded volume. So, that is what is this B. And then there is the pressure itself is reduced because the particles are attracting each other, and that is this term. Okay. Okay. So, of course we have derived this for the interacting particles model, but there is a bigger lesson here. So, this way of approaching the problem, starting from a microscopic description and then deriving a phenomenological thermodynamic potential, is a very useful way to connect microscopics and macroscopic phenomenology. And what we have just achieved here is an example of this. So, we have got an explicit expression for the equation of state, of course, in a certain regime where this quantity N naught times lambda to the D is small, yet it is a very nice result in illustrating this idea that you can start from some microscopic description and connect to thermodynamics, and we know that this description is quite good because we know that many real gases are indeed described by van der Waals equation of state. Okay. So, how do we proceed from here? We have got the equation of state. Now, we know that phases and phase transitions are all contained in the thermodynamic potentials implied by these equations of state and whatnot. So, our next goal is to explore what are the points where this thermodynamic potentials will have some kind of non-analyticity or some crossing of different types of different minima of energy, whatnot. So, let us explore this. So, if we have P as a function of V, which we have seen in the last graph, in the last slide, let us plot this and see what we get. So, immediately you will see that if you look at the equations, if you stare at them a little bit, you will see that the equations imply the existence of a particular temperature and a pressure, which is called Pc and Tc. And if you are at temperatures which are much greater than Tc, then you will see that the P as a function of this specific volume is just this hyperbola, that is what is implied by the ideal gas. And what you will end up getting is that you will see that below Tc, the pressure versus specific volume has a region where the derivative of the pressure with respect to specific volume is greater than 0. But that is a bit problematic, right? So, how can the pressure increase if I increase the specific volume? So, this is not allowed. So, this regime, for example, between this point and this point is not a physically permissible state. So, what this suggests is that there is probably a phase here and another phase here, and there is some kind of phase transition that will separate these phases. And this point where the P versus V has vanishing derivative, the first derivative vanishes as well as the second derivative vanishes, is some kind of a critical point. Okay. So, we can actually look at the equations and use P as a function of V and set these two conditions that I mentioned, namely the derivative is first derivative of P with respect to V is 0 and second derivative of P with respect to V is also 0, and we can extract what are the values of Tc. So, the Tc turns out to be this quantity. 8 by 27 is a bunch of numbers. A by B, remember A was related to the interaction strength and B was related to the volume, interaction strength times the radius of the volume of the hard sphere, and B was simply radius of the volume of the hard sphere again, sorry. And therefore, what you find is that this Tc itself is proportional to this U, and this Vc is just 3 times the quantity B, and Pc is of course related by the equation of state, and Pc turns out to be this quantity. So, okay, you may say, what is the big deal about this? The big deal about this is that you see there are 3 parameters here, Tc, Vc and Pc, but they are determined by 2 numbers, A and B. Okay. So, what you could do, for example, is you could pause the video and you can just derive these things so that you get a little bit more familiar with the terms and how they show up. In the next slide, I am going to show you a very interesting result. So, I am going to use the fact that these 3 parameters Tc, Vc and Pc are determined by 2 parameters A and B. So, what does that mean? That means that the parameters Tc, Vc and Pc are not independent. Of course, that is not surprising because Pc has to be determined by the equation of state. Okay. And what you will see, a simple calculation will show you that the theory shows that Pc, Vc by Tc is 3 by 8. So, this is something we can check experimentally. So, you can go out and you can find out the data. For argon, this quantity turns out to be close to 0.3. For carbon dioxide, it is somewhat, it's close to 0.3, and for all of these materials, it's sort of roughly close to 0.3. So in some sense this is a fantastic achievement, in the sense that by a very simple calculation we are able to show that the three parameters associated, three parameters in the phase diagram that you can get of any material, P, namely the critical pressure, critical specific volume and the temperature, they are related to each other in this fashion, and it seems that the experiment is quite close. They are more or less in the same ballpark. So for example, this didn't turn out to be 0.02, it's still a number which is close to 0.375 or so. And so this is a very interesting and very encouraging result. Okay. So the the theory with these two parameters is able to produce a critical point, is able to describe critical points of very different materials, and this is broadly in agreement with experiments. So here is a very nice exercise for you to do. You can do some literature search and figure out what are the reasonable values of R naught, U, etc. for argon, and then you can actually compute the values of TC, PC and compare it with experiments and see whether you get a good match. Okay, good. So we have established that there is a critical point, and from the PV curve and the fact that there is an unstable region in the PV curve, we have guessed that there are two phases below the critical temperature. And now we would like to find out what is the phase boundary. How if I look at, for example, the PT plane, where will I get the transition from the liquid phase to the gas phase or whatnot? Okay. So the liquid gas phase boundary in the PT plane is what we are after. So to do this, if you go back a few lectures, we discussed what are the correct thermodynamic potentials we should look at. So if you keep a system at constant temperature and pressure, at a fixed temperature and pressure, then the correct thermodynamic potential to look at is the Gibbs free energy per particle. So this is what I denote by G of T and P. Okay, we have computed the equation of state. So we know the pressure volume relationship at different temperatures. Question is, how can I get the free energy from that? Okay, so how do we do this? There are many ways to do this. I will indicate one way. So one way to do this would be, you first obtain the Helmholtz free energy. How do you obtain the Helmholtz free energy? You look at one of the thermodynamic relations. The change of the Helmholtz free energy is entropy times change of temperature minus pressure times change of specific volume. Now, at a fixed T, you will see that the change of Helmholtz free energy is minus PdV. So this is a very nice result, in that we can now calculate the free energy by integrating the equation of state, P as a function of V. I know P as a function of V, so I just integrate from infinity to V. Infinity is when specific volume goes to infinity, which means each particle is taking infinite volume, which means there are no particles in the system. Right, so I say something from vacuum to my current specific density, I do this integration, and so this W is a dummy variable for doing the integration. But you are a little disconcerted now, because this is an integral which looks like 1 by W, so it may not converge, because you know it's a log. Even when I do the integral here, I'll get a log, and then there's this infinite limit, so it seems to diverge. Okay, so this is a bit unfortunate, you may think, and you may get stuck here. But here I'll show you a very beautiful trick to circumvent this problem. So what you observe now is that if I put B equal to 0 and A equal to 0, then this must be the free energy of the ideal gas. So what I do is I take the expression for the free energy of the interacting system, the same trick that we did when we computed the virial coefficient A2, similar trick I should say. I add and subtract the free energy of the ideal gas. I keep the plus term that I am adding, the term that I am adding, I simply write the free energy of the ideal gas, which I can compute analytically. The term I am subtracting, which is minus T by W, that is exactly the same expression that I had for the van der Waals gas, where I have turned off B and A, which are the parameters of the van der Waals gas. So this is exactly the ideal gas relation. So I have added and subtracted the ideal gas free energy. So what do I get? I'll get this term now, which is T times W minus B minus T by W, which you will see will give a very nice convergent integral. So this integral will converge, and if you also recall what is the expression for the free energy of the ideal gas, we will find a very simple and nice expression for the free energy of the van der Waals gas, and that is what I have written out here. Okay. Okay. So maybe it's a good time to pause the video and sort of go through this calculation. I'm going to proceed. Okay. Now I need the Gibbs free energy. How do I get the Gibbs free energy from the equation of state? I have already got the Helmholtz free energy, and we know that the Helmholtz free energy plus P times V is the Gibbs free energy. So what do you mean by P times V? So what you have to do is, you have to find the specific volume associated with this pressure. That's what I mean. So you have to invert the equation of state in a way, right? And this V is a function of P here, and P times V, where V should be interpreted as something as a function of pressure. So V of P is a solution to the equation of state for a given pressure. So this is what is entailed in finding the Gibbs potential. Okay, very good. So now what we are going to do is we have derived the Gibbs potential, and I am going to show you now that when the temperature is below Tc, when the temperature is below the critical temperature, there are two possible values of specific volume for a given pressure, and that will give us two different Gibbs free energy values. Okay. So the first observation is that for T less than Tc and P less than Pc, the equation of state has two stable solutions. Now let me explain to you what stable solutions mean. So this is the P I have chosen, and the temperature I have kept at 0.85 Tc. So we are below Tc. So if I choose this pressure, you will see that the equation of state will give me three solutions, namely this value of V, which is a smaller value of V, and this is a larger value of V, and then there is yet another value of V sitting here, which is a solution to the equation, but at this point dP by dV is positive, and therefore this is what we call as an unstable solution, and these two are stable solutions. Okay, so what the equation of state has taught me is that at a given pressure below P critical and a temperature below T critical, there are two solutions, namely a small specific volume and a large specific volume. So it's very natural to see that the small specific volume is the specific volume of the liquid phase, the putative liquid phase, and Vg is the larger value is the specific volume of the gas. Okay. So what do I have to do now? I compute the free energies, the Gibbs free energies associated with the liquid by using this solution, and that of the gas by using the Vg solution here. So I get two different free energies at a given pressure and temperature. Which phase wins? The one with lower free energy. Okay. This whole setup that we have placed here will allow us to compute the phase boundary. Okay. So imagine that you are at a fixed temperature T less than Tc. How am I going to locate the phase boundary? I am doing it this way, you can do it other ways also. I am fixing the temperature and I am going to vary the pressure. And what I am going to do is I am going to plot the free energy of the gas solution and the free energy of the liquid solution. So you see, at low pressures I will get that the gas is the stable solution, and at high pressures I will get that the liquid is the stable solution, and there is a crossing, as it were, between these two free energies at a particular pressure which corresponds to the first order phase transition. And if I plot delta G, you will see that delta G will vanish. Delta G is free energy of gas minus free energy of liquid. You will see that it will vanish at this point, and that will allow us to locate the pressure at which the first order transition takes place at a particular given temperature. Okay. So, we have to look for the solution to the equation delta G, which is G gas minus G liquid. Which value of pressure does this vanish, and that will allow us to locate the phase boundary. Okay. So, I have gone ahead and computed this phase boundary in this fashion. So, this is P by P critical here, and on the x axis I have T by T critical, and you can see a very nice phase boundary between the liquid phase and the gas phase, and you should sort of think of this as a small sliver of this diagram. We have, of course, our approximations that we have made will not allow us to ask physically meaningful questions here because our approximations may not be correct. So, for example, this high temperature, low density, etc., those approximations will be questionable in the other side of the experimental phase diagram. But certainly our approach will allow us to access this part of the phase diagram, and you can see that it sort of produces nice results here. Okay. And what happens now is, if you work through this, you will see that as I go towards, as T goes towards Tc, this pressure will go towards the critical pressure, so it will also go to 1, and at this point the difference between the specific volume of the gas and the liquid will vanish. So, in some sense the distinction between liquid phase and gas phase will vanish, and you will get a critical point. Okay. So, before I tell you some interesting things about the critical point, I invite you to work out what is the latent heat of this condensation transition. If you say, for example, come down, right, or you can work out what is the latent heat, and you can sort of relate that to some slope of this curvature. Okay. So, we have got the phase diagram, and I am going to show you that we can do much more. We can even compute the critical properties. Remember, whenever I have a critical point, you get universal physics, namely you will get things that are independent of the microscopic details. So, let us see if that works out. So, we can now compute, for example, the compressibility of the gas and this quantity which is Vg minus Vl as a function of little t, which is the distance to the transition. So, this in this field is called as distance to the transition, namely T minus Tc by Tc. So, this is again, remember, a dimensionless number. And so, what I have done here is I have gone ahead and done this calculation, and you will see that when little t is positive, it diverges as t to the minus 1, and when little t is negative, it is also diverging as t to the minus 1. So, the critical exponent, what is called as gamma, we find from calculation is 1. And look at this quantity Vg minus Vl as I am approaching T minus Tc from the left side, namely from when this T is less than Tc, I am approaching Tc from below the critical temperature. So, this little t is negative, and you see it grows starting from Tc. As you reduce temperature, it grows as magnitude of T, little t, to the power half. So, what we have found is that we get critical exponents gamma equal to 1 and beta equal to half, which is a fantastic result, because the numbers 1 don't depend on argon, carbon dioxide and thing, they are universal. We have found that these numbers are same for all gases. They don't depend on U or R0, they don't depend on any of these parameters. And so, you might think that this is a fantastic achievement and you might want to celebrate, and you should, except you should pause and look at experiments. What does experiment tell you about beta and gamma? So, if you look at experiments, you will find that beta is not half, it is different from half. In fact, it's 0.326 plus minus something. And gamma is 1.24, and the remarkable thing which we have emphasized even in the very first lecture is that these values of beta equal to 0.326 and gamma is 1.24 etc. they have been confirmed to be same across materials, in the sense it could be variety of systems, whether it's argon, whether it is any other inert gas, whatever, they turn out to be these very close to these numbers, in the sense that they are universal, they don't depend on microscopic details, but they are different from what we found from our calculation. Our calculations are also giving universal answers, but they are different from what the experiment is showing us. And so this is a real puzzle now. Okay, so let's keep this puzzle in our mind and let's summarize the lecture. So what do we learn from the interacting particles model? Of course, we have found a phase diagram, we have found critical properties, etc. But what we have to learn from this at a larger level or a bigger level is that whenever you are faced with a problem and you are not able to solve it exactly for the set of parameters, it's a good idea to look for some small parameter and try to expand about the small parameter and try to solve the microscopic problem in some way. Once you are done with that, you will want to connect that with some phenomenological free energy or something like this, and then you can connect the phenomenology by using connecting statistical mechanics and thermodynamics, and from there you can actually derive phase diagrams, etc. So in some sense, in this chapter 4, we have explored a way of starting from microscopics and compute the phase diagram, compute critical properties and all of that. It is an interesting step forward, but we are also left with a puzzle. The puzzle is that our calculated critical exponents are not matching experiments. And if they are universal and don't depend on anything, why are they different from what we have calculated? So this is an interesting puzzle, and we hope to resolve this by the end of this course. And we will need to take many more steps before we get there. And the next thing we will do is we will study the Ising model, which is a very important model, as I have indicated several times in the previous lectures. We will start the study of the Ising model, and I am sure that you will join me for the next lecture. Thank you.